welcome to A Minute with a Molecule. The molecule here is NH3. Right next to it is another model of an NH3, and you have a whole lot of details. So I would like you to stop right here, take 1 minute, look at all of the information on this slide. At the end of 1 minute, I'm going to ask you to speak for as long as you can and try to explain everything on this slide. Then, of course, I will provide you with an exemplar answer. Let's take a look now at the answer. Let's start from the very diagram with the two models next to each other. Here you can see that we have a hydrogen bond. A hydrogen bond arises when you have polar molecules. The term hydrogen bonding is reserved solely for when nitrogen bonds with hydrogen, like here, or when hydrogen bonds to oxygen or to fluorine. So here we have this huge difference in electronegativity between nitrogen and hydrogen, which means that you have a polar bond. Electrons in this covalent bond are held closer to nitrogen than they are to hydrogen. So you have a small negative charge here developing on nitrogen and a small positive charge, delta positive, on hydrogen. This creates three polar bonds, but in addition to that, you have an overall molecular dipole which goes in this direction. This makes the ammonia molecule a polar molecule, and because it's a polar molecule, this negative side can bond here with this intermolecular force. The strongest of the intermolecular forces, of course, the hydrogen bond between these 2 points. Hydrogen bonding would mean that molecules like ammonia would have higher boiling points than molecules like pH3, which don't have hydrogen bonding, but have dipoles. Then we see here, we have some bond angles shown, and the bond angle here is less than 109.5, and here it's greater than 109.5. Let's think of the entire structure, including this lone electron pair here. Let's think of that entire structure and what shape it would make if we were to join all of these tips. And it would be tetrahedral. Tetrahedral, therefore, is its electron domain geometry. It's the geometry when you treat the lone pair of electrons here as a full domain, and you just join all of these points, you would get tetrahedral. But if we were to disregard the lone pair and then consider what molecular geometry or shape we would have, that is described as trigonal or trigonal pyramidal. And that is the molecular geometry of the ammonia molecule. Its electron domain geometry is tetrahedral. Here we have a lone pair. And of course, we note that lone pair bond pair repulsion is greater than bond pair repulsion. So therefore, that is why the angles in this ammonia molecule would be different from a CH4, a methane molecule, which is a perfect tetrahedron. Here we'll have a slightly greater than 109.5, and here slightly less than 109.5. Here we have a drawing of the Lewis structure of this model with nitrogen here, a lone pair up here, and three bonding pairs. Down here at the bottom we have the ammonia molecule drawn with its lone pair, and we have BF3, which is an exception to the octet rule, you might remember, with only 6 electrons in its valence shell. Here, of course, 3 from boron itself and sharing 1 here, not having a full octet. But BF3 is electron deficient, and it will have a tendency to attract electrons to itself. And the ammonia molecule has this lone pair right here, which it can donate. And being a lone pair donor makes it a nucleophile. It donates its electrons to this electron deficient center. And in donating its lone pair, it also behaves as a Lewis base, which is the definition of a Lewis base. And then, of course, it bonds with BF3 here. and it forms a covalent bond, but a special type of covalent bond called a coordination bond, where the lone pair of the nitrogen shares both electrons, and the coordination bond is represented as an arrow going this way. Ammonia also happens to be a Bronsted-Lowry base, which means that it can accept a proton. A hydrogen ion could actually become joined in here as well, and it would form the ammonium ion. And bases are proton acceptors, so ammonia is also a Bronsted-Lowry base. Ammonia can also, of course, behave as a ligand, which means it would donate its lone pairs to transition elements like copper, for example. And ammonia, of course, has covalent bonding between the nitrogen and the hydrogen here, a sharing of electrons. So that brings us to the end of this first episode of A Minute with a Molecule.